AN equal to BN, and the sum BN is divergent. Now, all the term be a positive, right? And the sum's divergent means what? This sum is going to go to infinity. And this sum is going to infinity. AN is bigger than BN means what? This sum is bigger than that. This is going to infinity. Of course, something bigger is going to go to infinity as well. Then sum of AN is divergent to infinity. That's what it's saying. Okay, this is the comparison test. The idea is you have a series that you want to study, you want to test, and you don't know what it is. But at least you can compare the unknown series to the series that you know already. Okay, and in order to have the comparison test, condition is what? All the terms need to be positive. All right. And there are two parts in the comparison test right here. The BN right here is the one that we know. And we want to learn about AN, right? So if this is convergent, and this is smaller than the convergent, BN is convergent, and the AN is smaller than the convergent series, it's going to be convergent. Okay? The other way is what? If this BN is divergent, and AN is even bigger than the divergent series, so AN is going to be divergent. Okay? Bigger than infinity, it's going to be infinity. All right? So let me give you an example. Example, say you want to learn about series 1 over n squared minus 1. Okay? And run from, say, now I have to say 2 to infinity, because 1 right here is going to be 0. Okay? My series starts from 2 to infinity. All right? And I do this one then. N squared plus 1 then. 1 to infinity. That's good enough. Okay? And I have no idea if this series is convergent or divergent, but I see this series kind of similar to something that I learned before. I'm thinking of this one, 1 over n squared. Alright? And I know this one is convergent. Okay? So this is like AN is equal to 1 over n squared plus 1. This BN is equal to 1 over n squared. Is it positive? Yes, positive. It's positive? Yes, it's positive. Okay? Because n is positive. N is starting from 1. So both are positive. Okay? And I see what this one is convergent. This is what I know. This is the P series. It is convergent. This is the P series. The P series. Okay? And P is equal to 2. Okay? So this is convergent. And let's compare the two terms. 1 over n squared plus 1. Is that smaller than 1 over n squared? Yes, because this have the same numerator. This denominator is smaller than that denominator, bigger than that denominator. So this fraction is smaller. So AN is less than BN. I'll write down here. AN less than BN. Okay. So I can use a comparison test. Say what? I have a positive series, okay, and a convergent positive series, and my new series right here is also positive and less than my convergent positive series. So this AN right here is convergent as well. So you can say that by the comparison test, this series right here is convergent. It's convergent. Okay. Okay. Let me show you another test called the limit comparison test. Number 2, limit comparison test. Okay. Again, I'm having still having the same two series, AN and BN. And run from 1 to infinity. And run from 1 to infinity. And both AN positive, BN positive. So 2 positive series. Now instead of comparing AN to PN, see which one is bigger, I'm going to make a ratio. I'll take the ratio of an over bn, and then I'll take the limit of that ratio when n goes to infinity. You can do an over bn or bn over an, okay, either way. And the limit, say, equal to a number c. Alright? Now, here comes the test. C is positive and finite. Then you say that the two series is behave the same way. That's how I say it. But the book, let me look at the book right to say what. If ABN is convergent, then AN is convergent. Okay, and vice versa. So let me write my way then. I'll do right. Positive and finite, then two series AN, BN, both convergence or divergence. Okay. It means what? If this limit is equal to a positive constant, then the two series behaves the same way. This is usually I say it, but it's not a formal way. That's the book writes, so I'm not writing it here. It means what? If this is convergent, then that is convergent. If this is divergent, that's divergent. So you have a series that you know, and you want to compare that series to something that you don't know, okay? And you take a ratio, the two general terms is if that limit is equal to a positive constant, and the two series gonna behave the same way. If one is convergent, the other is convergent. One is divergent, the other is divergent. Okay. Okay. So if C here is equal to 0, then inconclusive. You have no idea. So inconclusive. So you don't know it's convergent or divergent. Okay. So for the second type of comparison test right here, it's called the limit comparison test. Instead of compare AN to BN, what are we doing in here? We are taking the ratio of AN to BN, and we take the limit of that ratio go to, when that angle to infinity. See the behavior of that ratio. And that constant positive, but not go to infinity, positive and finite, then two series are going to behave the same way. If equal to 0, we have no idea. Okay, so example. I'm going to use the same example that we had before. Test for conversion diversion of the series 1 over n squared plus 1. Okay? This one right here, I claim we can use what the integral test would work. The comparison test would work. You compare to this series right here. Okay? You can compare. Now I'm going to show you how to work with this one using the limit comparison test. Alright, so instead of comparing this number to that number, this is, by the way, AN is equal to 1 over n squared plus 1. This is BN equal to 1 over n squared. I'm going to take in a ratio, AN over BN, which is 1 over n squared plus 1 over 1 over n squared. Divide by fraction means multiply by its reciprocal. This is equal to n squared over n squared plus 1. Now I'm going to take the limit of that thing. Limit of n squared over n squared plus 1 when n go to infinity. Alright, you can use L'Hopital rule in here. You learned that already in Calc 1. Okay, if not, then divide the top and the bottom by n squared. This is equal to 1. I can modify the fraction as well. N squared over n squared divided by n squared plus 1 over n squared over n squared. This is the limit, right? N go to infinity. If I don't know L'Hopital rule, I'll do it this way. It's the limit 1 over 1 plus 1 over n squared. N go to infinity, and this is equal to 1. So C equal to 1. Positive and finite. And that means the two series is going to behave the same way. C is equal to 1 here is positive, okay? And you know the two series behave the same way. This series right here, you know, is already is convergent, so you can give conclusion. This one is convergent as well. Okay. So what is the difference between the comparison test and the limit comparison test? For this two examples right here, I claim you can use both comparison test and limit comparison test. And if you see the example that I gave you before, but this one right here, now what is we can't use the comparison test directly yet because that fraction right here is actually bigger than that fraction. Okay? And this is conversion. We don't know if this is conversion or diversion. Something that bigger than a conversion series, it could be conversion or diversion. But if you do the limit one, then it's going to work. It's minus in here, minus right there, it's minus right there, the limit is still 0. And the two series still behave the same way. Okay? So, in my personal opinion, I would prefer the limit comparison test over the comparison test itself, even though it seems like we do a little bit more work, but in my opinion, it is more powerful. So, in this section, we show you two tests, the comparison test and the limit comparison test for you guys to use. Okay. And one thing about the limit comparison test, you will need to know some series in advance before you can use the comparison test, because you see, you have to compare to something that you know, right? So you compare this series to the thing that you know. So you have to know some series in advance. And the idea is you can compare some series, two series that look similar to each other. Go back to another example. Say n plus 1. Then this one, 1 over 1 over n. Okay? N from 1 to infinity. N from 1 to infinity. You see that this series is divergent, the harmonic series right here, 1 over 1 plus 1 over 2. And this kind of similar, right? And this one is also divergent as well. You can use the comparison. I'm not sure about the comparison test, but I can use the limit comparison test. I can take the ratio 1 over n plus 1 divided by 1 over n, and this is n over n plus 1. And if I take the limit of that thing when n go to infinity, this thing going to go to 1. My c right here is 1 positive, so the two series going to behave the same way. This is divergent, so that one going to be divergent. Okay. So the nutshell is you are looking back at this. And what I'm trying to say, you may see something complicated. Say square root of n squared plus 1, for example. So how to simplify to think of it in the big picture. It looks like square root of n squared, right? Square root of n squared is like n. So this is going to be similar. Square root of n squared plus 1 is kind of 1 over n squared, which is 1 over n. The two series going to behave the same way. That's what we're trying to say. Not just n squared plus 1, n squared plus 2n plus 3, for example. The highest sum is n squared. You take square root, it's just n. That was the idea. So whenever you guys see those type of problems, test for conversion or diversion of this series right here, you guys should think of the limit comparison test. Compare this one to 1 over n. That should work. Okay? And when you guys do the homework, any question, make sure that you ask. I'm going to leave that blank for you. Okay? So before we start, let me just summarize what we learned so far. I'm showing you two types of tests to test for conversion or diversion of series. The first test that we learned in 11.3 called the integral test. And we're going to compare the series to the integral from 1 to infinity. Condition is what the function needs to be positive, continuous, and decreasing. And whatever you know about the integral is going to happen the same way to the series. Another way, the integral is conversion, the series is conversion, and vice versa. The integral is diversion, and the series is diversion. And then 11.4, we talk about comparison tests. We have two types of comparison tests. The first comparison test, you compare the two series, which one is bigger. You know the series is conversion now. Condition is what? Positive series, okay? If the conversion series is bigger than the series, the unknown series, and the unknown series got to be conversion as well because it's smaller than a finite number. Of course, all positive. And the second case, what? If the known series is divergent and the unknown series is even bigger than the divergent series, then it's got to be divergent as well. Something that bigger than infinity got to be infinity. And about the limit comparison test, you are taking the ratio of the two general terms, an over bn, and you take the limit when n go to infinity. And if that limit is strictly positive, means bigger than 0, but finite, then what? The two series are going to behave the same way, both convergent or both divergent. If the limit equal to 0, well, we cannot say anything. Sometimes it's convergent, sometimes it's divergent. It's different. Maybe it's the same, maybe different from the series you compare it to. Okay? So that is about the comparison test. And of course, there's going to be more tests coming up, or the next couple sections, and you guys are going to see more powerful tests coming up. All right, but it's good for now. It's 11.4. I'm going to stop the clip right here. Thank you for watching, everyone. One more time. Any question, please feel free to ask. Have a good day.